Hi. Today I'm going to tell you 100 sleepy facts about the Northern Lights, perfect if you want to relax a bit and learn something interesting about this magical natural phenomenon. Enjoy listening. Hi. Today I'm going to tell you 100 sleepy facts about the Northern Lights, perfect if you want to relax a bit and learn something interesting about this magical natural phenomenon. Enjoy listening. 1. Aurora Borealis and Aurora Australis are natural light displays. The Northern Lights, Aurora Borealis, and Southern Lights, Aurora Australis, occur near the Earth's magnetic poles. They are caused by charged particles from the Sun colliding with the Earth's atmosphere. These collisions excite atmospheric gases, producing bright, colorful lights. They are some of the most spectacular natural phenomena visible from Earth. 2. Auroras occur in the ionosphere. The ionosphere is a layer of the Earth's atmosphere located about 60 to 600 kilometers, 37 to 373 miles, above the surface. Here, solar wind particles interact with oxygen and nitrogen. This interaction produces the shimmering light patterns seen in auroras. The high altitude means these lights can be visible over wide areas. 3. Solar wind powers the auroras. Auroras are driven by the sun's constant stream of charged particles called solar wind. When these particles reach Earth, they are guided by the magnetic field toward the poles. The energy from collisions with atmospheric gases is what creates the glowing colors. Without the sun's activity, auroras would be far less frequent. 4. Earth's magnetic field shapes auroras. The planet's magnetic field funnels charged particles toward the poles. This is why auroras appear mostly at high latitudes. The magnetic field protects most of the Earth from the solar wind, concentrating energy where the field lines converge. This is why you rarely see auroras near the equator. 5. Oxygen produces green and red auroras. When solar particles collide with oxygen atoms, they emit green or red light depending on altitude. Green is most common around 100 to 150 kilometers, 62 to 93 miles, above the surface. Red light occurs at higher altitudes above 200 kilometers, 124 miles. These colors dominate the auroral displays seen in most photos. 6. Nitrogen produces blue and purple auroras. When charged particles excite nitrogen molecules, blue or purplish light is produced. Blue light often appears at lower altitudes, while purple can appear in combination with red at higher altitudes. Nitrogen colors add depth and variety to auroras, making them visually stunning. 7. Auroras are not limited to Earth. Other planets, including Jupiter, Saturn, and even Mars, also experience auroral phenomena. On Jupiter, auroras are enormous and permanent due to its strong magnetic field. Studying planetary auroras helps scientists understand how magnetic fields interact with solar wind across the solar system. 8. Aurora shapes are influenced by magnetic storms. Auroras can appear as arcs, curtains, spirals, or even diffuse glows. Solar storms intensify auroras, stretching them across the sky. The shape changes rapidly as the magnetic field responds to incoming particles. This dynamic motion is part of what makes auroras mesmerizing. 9. Auroras can occur at lower latitudes during strong solar storms. Rarely, strong geomagnetic storms can push auroras far from the poles. In extreme events, people in the U.S., Europe, or Asia may see northern lights unexpectedly. These occurrences are often linked to massive solar flares or coronal mass ejections. 10. Auroras are best seen in winter months. The long nights of winter in polar regions make auroras easier to observe. Clear skies and low light pollution are also crucial. During polar summer, the sun never fully sets, making auroras hard to see even if they occur. 11. Aurora intensity depends on solar activity. The sun follows an 11-year cycle of activity. During solar maximum, auroras are brighter and more frequent. Solar minimum produces fewer displays, although auroras still occur. This cycle allows scientists to predict the best times for aurora viewing. 12. Auroras produce sounds in some rare cases. Some observers report hearing crackling or hissing sounds during very strong auroras. Scientists are still studying this phenomenon, as the sounds are faint and difficult to detect. They may be caused by electrical interactions in the lower atmosphere. 13. Aurora colors vary with altitude. Green auroras typically occur at mid-altitudes, red above, and blue or purple below. This layering is caused by the type of gas and the energy of incoming particles. Sometimes, multiple colors appear simultaneously, creating a multicolored display. 14. Auroras have been observed for thousands of years. Historical records from ancient China, Europe, and the Americas describe strange lights in the sky. They were often interpreted as omens or spiritual phenomena. Modern science now explains these events as solar particles interacting with the atmosphere. 15. Auroras can form spiral shapes. The charged particles follow curved paths along the magnetic field lines. This causes the lights to twist into spirals and curtains. Long-exposure photography captures these shapes in spectacular detail. Spirals are a signature feature of dynamic auroral displays. 16. Aurora displays can last from minutes to hours. Some auroras appear briefly as a flicker, while others persist across the night sky. Their duration depends on solar activity and the density of particles. Observers in polar regions often experience extended shows of auroral light. 17. The first scientific study of auroras was in the 1600s. Astronomers like Galileo and later Anders Celsius studied the patterns and periodicity of auroras. They linked the phenomena to magnetism and later to the sun's. Scientific understanding has grown substantially since these early observations. 18. Auroras can interfere with radio communications. Strong geomagnetic storms causing auroras can disturb radio and GPS signals. This is because charged particles affect Earth's ionosphere. Pilots, ships, and satellites must sometimes adjust operations during strong auroral events. 19. Aurora photography requires long exposures. To capture the faint lights, photographers often use exposures of several seconds to minutes. High ISO settings and wide-angle lenses improve visibility. The resulting images reveal patterns invisible to the naked eye. 20. Aurora forecasts are now possible. Space agencies monitor solar wind and magnetic field data to predict aurora activity. Apps and websites provide alerts for when northern or southern lights may be visible. This allows enthusiasts to plan trips for the best viewing opportunities. 21. Auroras are caused by charged particles from the sun. These particles, mainly electrons and protons, travel along the solar wind. When they collide with gases in Earth's atmosphere, they transfer energy to atoms and molecules. The energy is released as light, creating auroras. The intensity and colors depend on particle density and energy. 22. Auroras are more common near the magnetic poles. Earth's magnetic field directs charged particles toward the poles. As a result, auroras frequently appear in regions like Norway, Alaska, Canada, and Antarctica. The magnetic poles act like funnels, concentrating the solar wind. This explains why auroras are rare in tropical regions. 23. Aurora borealis is visible in the northern hemisphere. The northern lights are often seen in Canada, Alaska, Scandinavia, and Russia. Tourists travel from around the world to witness them. The name Borealis comes from Boreas, the Greek god of the north wind. It highlights the connection between the phenomenon and northern regions. 24. Aurora australis is visible in the southern hemisphere. The southern lights occur in Antarctica, New Zealand, and southern parts of Australia. Australis refers to the south. While less accessible to tourists than the north, the southern aurora is equally spectacular. Its patterns mirror those of the northern aurora, following the magnetic field. 25. Auroras can appear as curtains. Many auroras form curtain-like shapes, with folds and waves of light. These are caused by magnetic field lines guiding the solar particles. The movement of charged particles creates a flowing appearance. Long-exposure photos capture the full elegance of these curtains. 26. Auroras can appear as arcs. Sometimes, auroras stretch across the sky as long arcs. These arcs often extend hundreds of kilometers. They are usually stable and glow steadily. The arc shape occurs when particles follow smooth magnetic field lines. 27. Auroras can appear as spirals or rays. Dynamic auroras often twist into spiral patterns or radiate as rays from a central point. These movements are caused by turbulence in the magnetosphere. The rays correspond to particles traveling along magnetic field lines. Observers often see them moving or shimmering in real time. 28. Auroras can occur during geomagnetic storms. Strong solar activity triggers geomagnetic storms, which intensify auroras. During these storms, lights become brighter and appear at lower latitudes. These events are sometimes called aurora outbreaks. They provide excellent opportunities for scientists and photographers. 29. Auroras are linked to the sun's 11-year cycle. The solar cycle affects the frequency and intensity of auroras. During solar maximum, sunspots increase, and solar storms are more common. This leads to more spectacular auroral displays. During solar minimum, auroras are less frequent but still occur near the poles. 30. Auroras can produce different colors. Green is the most common color, caused by oxygen at mid-altitudes. Red appears at higher altitudes from oxygen, and blue or purple comes from nitrogen. Rare combinations create multicolored displays. The mixture of gases and altitude determines the final palette. 31. Auroras are sometimes silent. Most auroras do not produce sound. This is because they occur high in the atmosphere, too far for humans to hear. However, in rare cases, faint crackling or hissing has been reported. Scientists are studying these sounds to understand their origin. 32. Auroras have inspired myths and legends. Ancient civilizations interpreted auroras as spirits, omens, or gods' messages. Vikings believed the northern lights were reflections from Valkyries' shields. Indigenous peoples in North America had stories linking auroras to ancestors. These myths show how auroras influenced culture for centuries. 33. Auroras are caused by both electrons and protons. Electrons produce most of the visible auroras, especially green and red. Protons can produce faint purples and blues. Their interaction with atmospheric gases adds variety to auroral patterns. Studying particle types helps scientists understand solar wind effects. 34. Auroras are more frequent at night. Auroras are difficult to see during the day because sunlight overpowers them. The best viewing occurs in dark, clear nights. In polar regions, long winter nights provide extended opportunities. Nighttime also allows photographers to capture more vivid colors. 35. Auroras can occur in clusters. Multiple auroral structures can appear at once, overlapping and shifting. Clusters can create complex light shows. These patterns result from variations in magnetic field strength and particle influx. Observers often see rapidly changing, intertwined shapes. 36. Auroras are studied using satellites. Satellites monitor the sun's activity and Earth's magnetosphere. They help predict when auroras will occur. Instruments measure particle density, magnetic fields, and energy levels. This data improves forecasting and scientific understanding. 37. Auroras are affected by Earth's magnetic storms. During magnetic storms, auroras expand toward lower latitudes. These storms occur when solar wind pressure increases. The resulting auroras are brighter and faster moving. They reveal the dynamic relationship between the sun and Earth. 38. Auroras can occur in patches or bands. Sometimes lights appear as diffuse patches or long bands across the sky. These forms depend on the orientation of magnetic field lines. The patterns shift as the Earth rotates and solar wind conditions change. Photographers often capture bands stretching from horizon to horizon. 39. Auroras can be predicted hours to days in advance. Scientists track solar activity and use models to forecast aurora visibility. Satellites like NOAA's SCAR provide real-time solar wind data. Alerts inform enthusiasts when auroras may be visible. This predictive capability allows travelers to plan viewing trips. 40. Auroras are studied to understand space weather. Auroral activity reflects solar wind and magnetosphere conditions. By studying auroras, scientists learn about solar storms and radiation. This research is crucial for satellite protection and astronaut safety. Auroras serve as natural indicators of Earth's space environment. 41. Auroras are caused by energy transfer. When charged particles from the sun collide with atoms in Earth's atmosphere, they transfer energy. This energy excites the atoms, causing them to emit light. The process is similar to how neon signs glow on Earth. The energy transfer determines the brightness and color of auroras. 42. Aurora curtains move with the wind in the upper atmosphere. The auroral lights are shaped by electric currents in the ionosphere. These currents flow along magnetic field lines, causing the curtains to shimmer and ripple. The motion can be slow or fast depending on particle density. Observers often describe the movement as waves or flowing fabric in the sky. 43. Auroras can be green, red, blue, or purple. The specific colors depend on which gas is excited and at what altitude. Oxygen produces green and red lights, while nitrogen produces blue and purple. Rare combinations create multicolored displays. The color variation makes each aurora unique. 44. Aurora visibility depends on solar wind intensity. Stronger solar wind leads to more intense auroras. During solar storms, auroras can appear farther from the poles. The intensity also affects how bright and colorful the lights appear. Monitoring solar wind helps scientists predict auroral activity. 45. Auroras are influenced by Earth's magnetic storms. Geomagnetic storms can expand auroral zones toward lower latitudes. This means people in regions not usually experiencing auroras may see them. Strong magnetic storms can produce spectacular auroras visible across entire continents. They demonstrate the interaction between the Sun and Earth's magnetic environment. 46. Auroras can form pulsating patches. Pulsating auroras appear as small, glowing spots that blink on and off. They usually occur in the evening hours. The blinking is caused by fluctuations in the energy of incoming solar particles. Pulsating auroras add dynamic variety to the light show. 47. Auroras can appear as rays or columns. Auroral rays extend vertically and sometimes stretch hundreds of kilometers. They are aligned with magnetic field lines. Columns can appear stationary or flicker depending on particle activity. Rays and columns create the characteristic curtain effect seen in auroral photography. 48. Auroras are affected by seasonal changes. Auroras are more frequent around the equinoxes. During spring and autumn, Earth's tilt allows solar wind to interact more efficiently with the magnetic field. This increases the chances of bright displays. Winter provides long nights, but equinoxes provide optimal geomagnetic conditions. 49. Aurora forecasts are now accessible to the public. Websites and apps provide real-time data and predictions. They use satellite measurements of solar wind speed, density, and magnetic orientation. Enthusiasts can track auroral activity and plan viewing trips. Forecasting has made aurora tourism increasingly popular. 50. Auroras can occur at altitudes of 80 to 600 kilometers. The lowest auroras occur around 80 kilometers, while the highest can reach 600 kilometers. The altitude affects both color and intensity. Lower auroras often appear blue, while higher ones may appear red. This vertical variation adds depth to auroral displays. 51. Auroras occur due to collisions with atmospheric gases. When energetic particles collide with oxygen and nitrogen atoms, electrons are excited. These electrons release photons when returning to their normal state. This process produces the visible glow of auroras. The type of gas and energy level determines color and brightness. 52. Auroras are stronger during solar maximum. The Sun's 11-year activity cycle influences auroral intensity. During solar maximum, sunspots and solar flares increase. This produces more energetic solar wind, resulting in frequent, bright auroras. Observers can expect the most spectacular shows during peak activity. 53. Auroras can create diffuse glows. Sometimes auroras appear as soft, spread-out glows rather than distinct patterns. These occur when particles are less concentrated or more spread out. Diffuse auroras provide a gentle, atmospheric light effect. They contrast with the sharp, dynamic rays and curtains of more active displays. 54. Auroras can trigger radio signal disruptions. Strong auroras can disturb Earth's ionosphere. This affects radio waves and GPS signals. Pilots, satellites, and emergency services must account for these effects. Studying auroras helps mitigate risks to communication systems. 55. Auroras can be seen from space. Astronauts aboard the International Space Station, ISS, can view auroras from above. From space, auroras form circular patterns around the poles. These views reveal the full scale of the phenomenon, impossible to see from Earth. Space observation has greatly enhanced aurora research. 56. Aurora shapes can change rapidly. Auroras are highly dynamic, changing shape in minutes or seconds. The shifting magnetic field lines and particle fluxes cause constant movement. This makes auroras unpredictable and visually stunning. Time-lapse photography captures this dynamic motion beautifully. 57. Auroras can produce sounds at close proximity. While rare, some observers report faint crackling or hissing sounds. These sounds may be caused by electrical discharges near the ground. The phenomenon is not fully understood. Research continues to determine under what conditions auroras generate audible sounds. 58. Auroras inspire art and culture. Auroras have influenced folklore, paintings, and music. Northern cultures often associated auroras with spirits or gods. Modern artists capture their beauty in photography, painting, and digital art. They remain a source of inspiration for millions worldwide. 59. Auroras are linked to space weather monitoring. Auroral activity is a key indicator of solar storms and space weather. Studying auroras helps scientists predict radiation storms. This information is critical for satellite safety and astronaut missions. Auroras provide a natural window into Earth's space environment. 60. Auroras can occur in clusters or diffuse patches. Sometimes, multiple auroral structures appear simultaneously. These can be tightly packed rays, arcs, or soft glows. The clustering results from variations in particle density and magnetic field configuration. Observers often see complex patterns in the sky during strong activity. 61. Auroras can be affected by coronal mass ejections, CMEs. CMEs are massive bursts of solar wind and magnetic fields from the Sun. When they reach Earth, they can trigger intense geomagnetic storms. These storms produce brighter and more widespread auroras. Scientists monitor CMEs closely to predict aurora activity and protect satellites. 62. Auroras are named differently in each hemisphere. The northern lights are called Aurora borealis, while the southern lights are Aurora australis. Borealis comes from the Greek god of the north wind, Boreas. Australis means southern in Latin. The distinction reflects their geographic visibility near the respective poles. 63. Auroras can form diffuse arcs along the horizon. These horizontal arcs often appear before more dramatic displays. They are caused by low-density particle flows interacting with the upper atmosphere. Observers may notice faint glows stretching across the sky. These arcs often serve as precursors to more dynamic auroras. 64. Auroras can have pulsating forms. Pulsating auroras flicker on and off in rhythmic patterns. They usually occur at lower intensities than full auroral displays. The pulsations correspond to periodic changes in incoming solar particle flux. This effect adds a mesmerizing, almost musical quality to auroras. 65. Auroras can extend beyond the polar regions. During strong geomagnetic storms, auroras can appear at mid-latitudes. People in Europe, North America, and even Japan have reported seeing auroras far from the poles. These rare events highlight the Sun's power and influence over Earth's magnetic environment. 66. Auroras can occur on other planets. Jupiter, Saturn, Uranus, and Neptune all have auroral phenomena. On Jupiter, auroras are permanent and very large due to its strong magnetic field. Studying auroras on other planets helps scientists understand planetary magnetospheres and solar wind interactions. 67. Auroras are influenced by the tilt of Earth's magnetic axis. Earth's magnetic axis is tilted relative to its rotational axis. This tilt changes the position and intensity of auroras throughout the year. Seasonal variations affect where auroras are visible and how bright they appear. The tilt also causes auroras to shift slightly in location over decades. 68. Auroras can appear in unusual shapes like spirals or curtains. The charged particles follow curved magnetic field lines, creating intricate patterns. Spirals twist and fold like ribbons in the sky. Curtains ripple and shimmer as particles move along the ionosphere. These dynamic shapes are signature features of auroral displays. 69. Auroras can vary in brightness. Some auroras are faint and barely visible to the naked eye. Others are so bright they illuminate the landscape. Brightness depends on solar wind intensity and particle density. Observers often judge aurora activity by comparing brightness to familiar objects. 70. Auroras can produce red edges. High-altitude oxygen can emit red light, often forming the outer edge of an auroral display. The red glow is rarer than green and usually occurs above 200 kilometers (124 miles). It adds depth and visual complexity to auroras. Photographers especially value red hues in images. 71. Auroras can be symmetrical between hemispheres. Auroras often mirror each other across the northern and southern hemispheres. This symmetry is due to the global structure of Earth's magnetic field. Observing this symmetry helps scientists understand magnetospheric dynamics. It also illustrates the interconnectedness of Earth's polar regions. 72. Auroras can interact with clouds. Clouds can obscure auroras, but sometimes they reflect and diffuse the light. This creates unique visual effects, including glowing skies and shadowed patterns. Observers may see auroras behind clouds, adding depth. Cloud interaction can enhance photographs artistically. 73. Auroras are affected by local magnetic anomalies. Some regions of Earth have irregular magnetic fields. These anomalies can distort auroral patterns locally. Observers in such areas might see auroras in unexpected shapes. Studying these effects helps map local variations in Earth's magnetic field. 74. Auroras can appear in multiple layers. Auroral displays sometimes show several distinct layers of light. Each layer corresponds to different altitudes and particle energies. Lower layers may appear blue, middle layers green, and upper layers red. Layering adds three-dimensional depth to the display. 75. Auroras can influence animal behavior. Some animals, particularly birds and migratory species, may react to bright auroral displays. Changes in magnetic fields can affect navigation. While research is ongoing, auroras may temporarily alter animal movement patterns. This shows that auroras have ecological as well as visual impacts. 76. Auroras can produce faint radio emissions. The interaction of charged particles with the ionosphere can generate very low-frequency, VLF, radio waves. Scientists can detect these emissions using special equipment. They provide another way to study auroras. This helps understand electrical currents in the magnetosphere. 77. Auroras can indicate solar storm severity. The brightness and size of an aurora can reflect the strength of an incoming solar storm. This visual cue can serve as an early warning for space weather. Researchers combine aurora observations with satellite data for forecasting. It's an example of natural phenomena aiding scientific monitoring. 78. Auroras are stronger near the magnetic poles, not geographic poles. Auroral ovals form around the magnetic poles, which are offset from geographic poles. This is why auroras in some locations are more frequent than in others at the same latitude. Magnetic positioning determines the likelihood of seeing auroras. Travelers often use magnetic maps to plan aurora trips. 79. Auroras can influence electricity grids. Geomagnetic storms that produce auroras can induce electric currents in power lines. These currents can damage transformers and other infrastructure. Understanding auroras helps engineers protect electrical systems. It shows how solar phenomena can affect technology on Earth. 80. Auroras inspire scientific and artistic observation. Auroras continue to captivate scientists, photographers, and artists alike. They provide insights into Earth's magnetosphere and solar activity. They also offer endless inspiration for visual and literary arts. Their combination of science and beauty makes auroras unique in the natural world. 81. Auroras can occur in oval-shaped zones around the poles. These auroral ovals are centered on Earth's magnetic poles rather than the geographic poles. They typically span latitudes from 65 degrees to 75 degrees. The oval shape results from the geometry of Earth's magnetic field. Stronger solar storms can expand the ovals toward lower latitudes. 82. Auroras can be seen from airplanes. Flying at high altitudes reduces atmospheric interference and light pollution. Passengers on polar flights sometimes witness auroras from above. This view provides a unique perspective of auroras stretching across the horizon. Some airlines even advertise aurora viewing flights in winter. 83. Auroras are sometimes used in scientific studies of the ionosphere. Auroras help researchers understand the behavior of charged particles in the upper atmosphere. By analyzing auroral patterns, scientists can study ionospheric currents. This data contributes to satellite navigation, communication, and space weather prediction. Auroras are thus both beautiful and informative. 84. Auroras can affect satellite operations. Strong geomagnetic storms that produce auroras can disrupt satellite electronics. Satellites may experience communication interruptions or increased drag in low Earth orbit. Operators monitor space weather forecasts to minimize damage. Auroras indirectly highlight the importance of protecting space infrastructure. 85. Auroras can appear simultaneously in both hemispheres. Because Earth's magnetic field connects the poles, auroras often mirror each other in the north and south. Simultaneous displays can provide global data for researchers. This symmetry demonstrates the global influence of solar wind on Earth's magnetosphere. It also creates spectacular visual experiences for observers in both hemispheres. 86. Auroras can be captured using long-exposure photography. Long exposures allow cameras to collect more light than the human eye can see. This captures faint auroral details and colors. Photographers often use tripods and wide-angle lenses for the best results. Long-exposure images reveal structures, movements, and colors invisible to casual viewers. 87. Auroras are brighter during geomagnetic substorms. Substorms are short-lived disturbances in Earth's magnetosphere. They cause particles to accelerate, producing intense auroral displays. Substorms can last from minutes to a few hours. Observers often notice rapid movement and flickering during these events. 88. Auroras have inspired myths across cultures. Different cultures have interpreted auroras in unique ways. Vikings thought they were reflections of Valkyrie's armor. Indigenous peoples in North America believed they were spirits of ancestors. Modern interpretations continue to emphasize beauty, mystery, and scientific curiosity. 89. Auroras can be green at mid-altitudes. Green light is most common and occurs between 100 to 150 kilometers above the surface. It is produced by oxygen atoms excited by solar particles. This color often dominates auroral displays. The prominence of green makes it the signature color of auroras worldwide. 90. Auroras can produce red hues at high altitudes. Red auroras occur above 200 kilometers, caused by high-altitude oxygen emissions. They are less common than green but highly prized by photographers. Red auroras often appear at the tops of auroral curtains. Their rarity makes them an exciting sight for observers. 91. Auroras can appear blue or purple. Nitrogen molecules create blue and purple auroras, usually at lower altitudes. The blue occurs when high-energy particles excite ionized nitrogen. Purple appears when red and blue emissions combine. These colors add depth and variation to auroral displays. 92. Auroras are strongest during the equinoxes. Auroral activity peaks in spring and autumn due to Earth's magnetic orientation. During equinoxes, solar wind interacts more efficiently with the magnetosphere. Observers at high latitudes are likely to see brighter and more frequent auroras. This seasonal pattern helps plan aurora watching trips. 93. Auroras can appear diffuse or structured. Some auroras form faint, spread-out glows, while others are structured with rays or curtains. The structure depends on particle density and magnetic field alignment. Diffuse auroras may cover large areas but lack distinct shapes. Structured auroras create more dramatic visual effects. 94. Auroras can cause temporary GPS disruptions. Charged particles can disturb signals in the ionosphere. This may lead to navigation errors for GPS devices. Airlines, ships, and scientists track auroras to mitigate these effects. Space weather monitoring helps prevent long-term disruptions. 95. Auroras can be photographed in time-lapse. Time-lapse photography captures auroras' rapid movements and color changes. It reveals patterns that are invisible to the naked eye. Photographers often produce videos showing flowing curtains and spirals. This technique highlights aurora's dynamic nature. 96. Auroras are indicators of space weather conditions. Auroral activity reflects the interaction between solar wind and Earth's magnetosphere. Scientists use auroras to monitor geomagnetic storms. This helps predict radiation exposure for astronauts and satellite systems. Auroras act as visual markers of solar-terrestrial interactions. 97. Auroras can appear as arcs, rays, curtains, or spirals. Different magnetic and particle conditions produce various auroral shapes. Arcs stretch across the sky, rays extend vertically, and curtains ripple like fabric. Spirals form during dynamic particle flows. Each shape adds to the beauty and complexity of auroral displays. 98. Auroras are brighter in areas with low light pollution. Urban lighting can obscure faint auroras. Observers in remote, dark locations often see more vivid displays. Clear skies and minimal artificial light improve visibility. Many aurora tours focus on rural or Arctic regions to maximize viewing. 99. Auroras are studied using ground-based observatories. Observatories track auroral activity with cameras, magnetometers, and other instruments. Data collected helps understand particle dynamics and geomagnetic storms. Ground observations complement satellite monitoring. Together, they provide a comprehensive picture of auroral phenomena. 100. Auroras are both a scientific and cultural wonder. They inspire awe, photography, mythology, and scientific research. Studying auroras enhances understanding of Earth's magnetic environment and space weather. Their unpredictable beauty continues to captivate people worldwide. Auroras remain a symbol of the mysterious interplay between the sun and our planet.